Okay, welcome everyone. Welcome. As the chair of the physics department, it is my pleasure to welcome you to the 2024 David M. Lee Historical Lecture in Physics. The David M. Lee Historical Lectures in Physics are sponsored by the Marvin and Annette Lee Fund. David M. Lee is Professor Emeritus of Physics at Cornell University and Distinguished Professor of Physics at Texas A&M University. He shared the 1996 Nobel Prize in Physics with Robert C. Richardson and Douglas Osheroff for their discovery of superfluidity in helium-3. He cannot attend today's lecture, but we are happy that his son Jim Lee and his grandson David Lee are here with us today. And now it's my pleasure to introduce Professor Frank Wilczek, Herman Feshbach Professor of Physics at the Center for Theoretical Physics at MIT, Chief Scientist at the T.D. Lee Institute and Wilczek Quantum Center at the Shanghai Jiao Tong University, Distinguished Professor at Arizona State University, and Professor of Physics at Stockholm University. Well, I first met him when I was a junior fellow here in the late 80s. He was visiting Harvard as a visiting faculty. I guess we were not lucky to have him stay with us, so there's no Harvard University in this list, unfortunately. Frank is a theoretical physicist, author, and intellectual adventurer. He has received many prizes for his work, including a Nobel Prize in Physics and Templeton Prize. Regarding his Nobel Prize, he's a very modest man, and he said after receiving it that I won't let my first Nobel Prize get into my head. Frank has made many seminal contributions to fundamental particle physics, cosmology, and the physics of materials. His current theoretical research includes work on axions, anyons, and time crystals. These are concepts in physics which he named and pioneered. Each has become a major focus of research worldwide. Frank has authored several well-known books and the monthly Wilczek's Universe feature for the Wall Street Journal. His latest book, Fundamentals, 10 Keys to Reality, distills the most profound and mind-expanding insights of modern science and explores their implications for questions that are usually considered philosophical or even theological. Frank received a BS at the University of Chicago in 1970 and a PhD in physics at Princeton University in 1974. He has been married to Betsy Devine, who's with us here since 1973, and they have 2 daughters. So I will not take any more time of yours, and I let Frank to give us a lecture.
Thank you very much for joining me on this festive occasion. I didn't quite know how to conceptualize this lecture. I've very rarely given historical lectures. I studiously avoid opportunities to do so. But Harvard is Harvard, and I decided to do it. And I conceptualized it as kind of a job talk. So I'll be advertising my career in QCD. I think it's interesting as physics as well as history, and I will include things that are still very lively topics of research in the physics community. So this is my title, My Life with QCD, and it's been a 50-year love affair that's still going strong, like my marriage. So to begin at the beginning, asymptotic freedom, which was my earliest work in physics altogether, I think it's fair to say, resulted in the birth of the new QCD. People can argue about the old QCD. I mean, Yang-Mills theory goes back much further, of course, and there were various hints of that you might want to have gluons, and then they might be vector particles, and there might be a color degree of freedom. But this was all talk, and very little in the way of calculations and no definite theory. The new QCD started in very identifiable way in 1973, started with a bang, as I'll describe. So there was a core calculation, and my interest in this was inspired, well, first of all, by the desire to get a PhD thesis. So looking around for a problem. And there was a famous problem. I didn't know very much physics. I transferred from mathematics. So I was looking for something that could be cleanly formulated and that used the kinds of mathematics that I knew about, symmetry and group theory and analysis. And there was this sort of thing was in the air because Ken Wilson was visiting Princeton, as was Sidney Coleman. And of course, David Gross was an enormous influence and my thesis advisor. David and I talked about many things, but the thing that kind of caught fire was this problem of quantum field theory. So that had the advantage, you didn't really have to know anything. It was an abstract mathematical problem, where when you calculate in a wide variety of quantum field theories, in fact, all quantum field theories that were analyzed at the time, you find this drastic phenomenon of screening. That is, if you put in a charge, and this is familiar in the case of electric charge, you put in a charge, it tends to polarize the medium around it, if it's in a medium, pull in charges that tend to cancel it. Okay, so its influence diminishes. This also occurs in a quantum mechanical theory in vacuum. You can think of these polarizable molecules as arising from virtual particle-antiparticle pairs. So they pop into and out of existence. But if you think of time coming out and take a slice, you'll always see this kind of distribution of charge that's influenced and can screen the charge in the middle. And what emerged from calculations is that this effect is very drastic. Often in quantum field theory, you have nearly divergent or divergent quantities, ultraviolet catastrophes. And here, what you find is that if you start with any finite charge at the origin, it gets completely screened. So if E at the origin is 0, then E off at infinity, the observable electric charge, is 0. And you can not only draw pictures, but you can also draw other kinds of pictures, Feynman diagrams that come with rules for how you evaluate the effect, and that's what you get. And you can also read it another way. That is, if you start out with any bare charge that's finite, then the renormalized charge is 0. So this was called, in Russia, this was famous as the zero charge catastrophe. Or it had another name, which is coming up, from Lev Landau. We are driven to the conclusion that the Hamiltonian method for strong interaction, that is quantum field theory, is dead and must be buried, although, of course, with deserved honor. So that was kind of generous to say. For technical reasons, this became known as the Landau ghost. If you continued the calculations to large momenta, you found a pole which has negative metric, so it's a ghost, and this was called the Landau ghost. So could we get rid of the Landau ghost, or was it a disease of quantum field theory that did, as Landau thought, doom the attempt to use it for the strong interaction? Well, in the early 1970s, there was a new kind of theory on the horizon, or a theory in the hands of Yang and Mills that was not usable for a long time until that Hooft and Veltman and others clarified its structure so that you could actually get finite answers from these unusual and redundant theories. I have gauge invariance, so when you calculate, you're in grave danger of calculating nonsense if that things that are gauge dependent. So all these technical problems and regulating consistent with the symmetry got pretty well understood in the early 70s. And it was straightforward in principle, therefore, to calculate how this phenomenon of screening, or this Landau ghost, would behave in these new kinds of theories that were available for theoretical exploration. And not only were they available, but they were being successfully used in the description of the weak interaction. So another way of phrasing the motivation is, what is the short distance or high energy behavior of the weak interaction? So a phrase which David often used in those days and I took up is straightforward in principle. I learned to loathe this expression because it usually meant that there was a very, very difficult calculation that he expected me to do that was really, in practice, usually only straightforward-ish. And in this case, we had to do a rather demanding calculation. Today's technology, with today's theoretical technology, and above all with the faith that you can get a sensible answer here when you combine the renormalization group and gauge symmetry, you can just calculate it, and there are many shortcuts and alternative ways. And if you know that there is a correct answer, especially if you know what the right answer is, you can easily derive it. But we didn't know the answer. And the algebra, as you can glean from these Feynman rules, is quite tricky. We also, because we were unsure of the foundations, wanted to calculate in arbitrary gauges. So that's this alpha parameter. We should get an answer that's independent of that parameter, even though it appears in all the intermediate steps. And also, you should get the same result for screening of different kinds of sources of charge, for the gauge bosons, for the fermions, and even for what's called the Faddeev-Popov ghost, which I'll come to momentarily. So the gauge bosons involved calculating all this stuff. Again, in arbitrary gauges, the Faddeev-Popov ghost which is basically the longitudinal gauge boson, the unphysical degree of freedom of the gauge bosons, also couples to the gauge boson. So you need to see that it has the same coupling constant, and the fermions also. All of these things needed to be calculated, and it had to be shown that it all made sense, that it was independent of this parameter alpha, and you got the same answer by calculating in many different ways. And that took a while, but at the end, it worked. And we found a very delightful result. The ghost was gone. In this kind of theory, you get anti-screening. And what happens is you have a charge that starts at an infinitesimal value and grows at infinity and shrinks towards zero at the origin instead of the opposite. So here are the actual equations. This is called asymptotic freedom. What the symbols mean is that you have an effective charge which depends on how closely you look. As t goes to infinity in this notation, you're looking closer and closer, so shorter and shorter distances, and the charge goes to zero with some group theory factors that depend on which gauge symmetry you're assuming and how many fermions you have and what their representations are. Anyway, we could get rid of this ghost. We were the Ghostbusters. Oh, I should say that I wanted to show these pictures here to emphasize that we were really young in those days. I mean, you look at me now and you say, how could this guy have been doing anything 50 years ago other than toddling around or maybe rumbling around in the mama's belly? But, you know, that was a more contemporary picture. All right. Okay, so that was kind of the quantum field theory problem. Now, let me show you how it got tremendously highly leveraged. I can't easily express to you how lucky we were that this kind of abstract discovery was so highly leveraged that it led us to a unique theory of the strong interaction. So this was kind of the origin story of the strong interaction, the famous, that there was such a thing, the famous Geiger-Marsden experiment. And what it was shooting alpha particles from a radioactive source at a gold foil and seeing how the alpha particles scattered. So here is a more abstract and perhaps illuminating picture of it. You have the alpha particle and it gets deflected. And depending on what the forces are, it has likelihood of getting deflected that is different. The stronger the force, the more it can recoil, the more likely large angle scattering is. So this is a way, by studying momentum changes, you get to study forces. And what Rutherford's analysis of this experiment by Geiger and Marsden showed was that Coulomb forces, amazingly, forces that had been known for a long, long time, governed the interior of atoms too, that you could account for the scattering, provided that inside these gold atoms was a heavy nucleus that had all of its positive charge and almost all of its mass. So this was used to determine a force, in this case the electromagnetic force, but also to show the existence of atomic nuclei and pose the problem, what holds those nuclei together? We needed a new force, the strong force, to hold it together against electrostatic repulsion. But the nucleus here was just a black box. In retrospect, the next step should have been clear, but hindsight is 20/20. This actually took more than about 60 years to get done. This was the next step was to look not only at spatial structure, but also, because we have a relativistic system with stuff inside moving very, very rapidly, change the energy so we can get resolution not only in space, but also in time. So this was called deep inelastic scattering. And whereas the Geiger-Marsden experiment was basically a tabletop experiment, I showed you the table and the thing. This one, because you wanted to take snapshots at much, much smaller scales, meant you had to study much, much larger momentum transfers. So you had to have particles which had that much momentum to begin with, and also large energy transfers. And so instead of a tabletop experiment, you had a 2-mile accelerator, the Stanford Linear Accelerator, where the crucial experiments were done. This, by the way, straddles the San Andreas Fault, but luckily that was relatively quiet at the crucial time. And this gives you a sense of the scale of the actual apparatus, so quite an evolution from the days of Rutherford and Geiger and Marsden. But these experiments were very, very revealing of the internal dynamics of protons and ultimately of the nature of the strong force. The first thing that emerged is that these snapshots came out very crisp. You could actually see structure inside the proton, individual particles that has the properties that people thought of as quarks, but also you could infer gluons. And the fact that you could see anything at all in this strongly interacting system indicated that the particles could get out, these elementary particles could get out without being too disturbed. They didn't get, the structure didn't get fuzzed out by interactions as things leave the protons or nuclei. So this was now reality, not just high theory, pointing us towards asymptotic freedom as a desirable property of not just quantum field theories to make them internally consistent, but specifically a theory of the strong interaction. So, and the only theories that served were the so-called non-abelian gauge theories, which are sort of grand generalizations of electrodynamics, but in which the photons also carry charge. But it left open the question of which non-abelian theory exactly should we be looking at. So we, that is David Gross and I, put a lot of effort into looking into conservative options. That was, conservative here means options, theories where the particles that appear in the Lagrangian, the ingredients of the theory, are actually the particles you see in the laboratory directly. That was the traditional approach to physics. But that doesn't work if you have massless charged particles, which are difficult to isolate at low energies. They lead to so-called infrared divergences, but we found nothing attractive along those lines. So in desperation, we kind of threw a Hail Mary pass, turning a bug into a feature that is the unknown low energy behavior of this kind of theory with massless charged particles. We said, well, if their massless charged particles are problematic to try to deal with as free particles, maybe they can't be free particles. And so we proposed the theory that came to be known as QCD, or quantum chromodynamics, and that, of course, to this day is accepted as the theory of the strong interaction. Now, it was important that right from the beginning, the new QCD, as opposed to all earlier ideas about the strong interaction, supported intricate calculations with testable consequences. This was something quite new. Now, the analysis was kind of complicated. To interpret those snapshots, you had to do quite a lot of image processing. You can imagine you scatter electrons, see how they bounce off, and then somehow you have to turn that into a picture of what's going on. And that goes through things like dispersion relations, current products, operator product expansion, scale-dependent mixing, and renormalization of operators. At the end of the day, though, it led to a very specific pattern of structure, of predictions for observable structures within the proton. So how the proton would look at different resolutions. And I did a lot of these calculations using Val Fitch's PDP-11, which maybe brings history to life, like nothing else. 50 years ago, this was the absolute cutting edge computer. Val Fitch, of course, was a famous experimentalist. He already had a Nobel Prize at that time. So he was able to afford a PDP-11, but at night it wasn't getting used. So I borrowed it, and he let me borrow it. And you can see the output was this kind of toilet paper with holes in it. Yeah, that's right. Anyway. Now, often there's a big gap between something being testable and actually being tested. I'm sure you're all familiar with this. Gravitational waves took 100 years Higgs particle took 50 years, anyons took 40 years, and so on. And so Higgs particle took over 50 years, and so forth. And my dear friend and mentor, Sam Treeman, in 1974, as we were making these quantitative predictions, they were predictions for how things would evolve logarithmically as you cranked up the energy. And Sam said, people never measure logarithms because you have to change the energy by a ridiculous amount in order to make the logarithm change a little bit. So I was gobsmacked when in my first workshop ever, so sort of my first exposure to the physics community, was Feynman was giving a keynote talk at Mickey Rooney's Tabas Hotel, also known as the Downingtown Inn in rural Pennsylvania. I don't know how many of you are old enough to remember Mickey Rooney, but he co-starred in movies with Judy Garland. And, well, you see here. It's the little things you remember. This was a place within the Downingtown Inn where you see an interesting sign there. Feynman walked up to this entrance, looked up at the sign, and strode right in, and then sort of challenged anyone else to do that. Anyway, subsequently, I was amazed and delighted. But he in his concluding talk, in his summary talk, advertised what we were doing very heavily and said, experimenters, you should go out and measure this. He didn't believe it was correct. I mean, he didn't believe it applied to nature at that point, but he said, you have to check it. And subsequently, I was amazed and delighted to witness the process of experimenters rising to the challenge, a very difficult, challenging thing to do accurate measurements, and crank up the energy, and see what was coming out of that PDP-11. It really matched. Very nice. So a striking implication of this is that at ultra high resolution, as you look at really, really short distances and really, really short times, the proton reveals more and more. You get more and more gluons, softer in energy, so more and more structure gets revealed. And this is an artist's impression that I love of a proton, where it sort of looks like a living cell with different organelles. It's all quarks and antiquarks and gluons, but they start to overlap, and they're very intricately related inside a proton. For this lecture, I went over the early papers and noticed that we also did something else, which reminded me that we spent at least as much time on this as on those core calculations, which was calculating what happens when you put scalar particles in the theory. This was the attempt to use spontaneous symmetry breaking to get rid of the massless charged particles. It never really worked very smoothly, but gave the PDP-11 another kind of workout, solving differential equations. And those calculations have been repurposed in many, many later investigations, including investigations of whether our vacuum is metastable and might decay someday, because you can diagnose the behavior at very short distances, and maybe there are instabilities there. Okay, so that's the early days. And let me draw a lesson from that to share as wisdom. At this point in my career, I'm supposed to have wisdom. So looking back, it's remarkable how much we learned by a process I called hopeful calculation. That is, we didn't understand what we were doing frankly. We had all kinds of issues about what to do about infrared divergences. What about this problem of confinement? Okay, the theory is written in terms of quarks and gluons. Where are the quarks and gluons in nature? We didn't have an answer to that, really. We had technical problems with gauge invariance, especially when we calculated the structure function evolutions. Lots of technical problems. Was this applicable to the actual strong interaction? And would these logarithmic things we were calculating ever be feasible to test experimentally? We didn't worry about it. We just calculated. Just learning by doing. We thought we would learn by doing. And years later, I realized that this wisdom was anticipated by the fortune cookie industry. This is a fortune cookie I love. The work will teach you how to do it. Sometimes this is paraphrased in a rather ugly way. Shut up and calculate. That's kind of rude, although it is pretty much the same thing. I prefer to say, calculate first, talk later. Then you might say, calculate first and think later, but that's going too far. All right. All right, so now I'm going to shift gears radically, go into a much higher gear to sort of survey the next 40 plus years of work, which I've continued to build on QCD in different directions and benefit from this wonderful gift that we were able to leverage a rather abstract theoretical phenomenon into the theory of the strong interaction. One thing that happened is that it opened up new horizons in cosmology. Sidney Coleman, a dear friend, who, by the way, played an important role in these early calculations. He was visiting Princeton, and we consulted with him quite a bit. He quoted, I think, Verlaine, anyway, some French poet, that we live in the age of the trembling of the veil. And I love that phrase. And that was very much the case in cosmology, as you can glean by comparing what Weinberg said about the early universe in 1972 versus what he said in 1976. So this made a huge impression on me because I studied this book as it came out at the time very carefully, and at the end was kind of a challenge. However, if we look back a little further to temperatures greater than 10 to the 12th Kelvin, we encounter theoretical problems of a difficulty beyond the range of modern statistical mechanics. This is when the people thought of the strong interaction as being a lot of hadrons, and they would start to overlap. They interact strongly. What do you do when you go back and have them very dense in the early universe? And nobody really knew. But in 1976, in the first 3 minutes, he said, the asymptotic freedom of these non-abelian gauge theories thus provides a solid mathematical justification for the very simple picture of the first hundredth of a second that the universe was made up of free elementary particles, the quarks and gluons. And the interactions got weaker, so you could actually calculate using controlled perturbative methods. Well, I had several adventures exploring this new open horizon in the whether you could explain the asymmetry between matter and antimatter in the early from events in the early universe, building on what I mentioned before about analyzing instabilities, but also other considerations, the possibility that we might live in an unstable or metastable vacuum based on quantum field theory. But the two things what I want to say a few more words about, and I think where my contributions are more distinctive, were in understanding QCD at high temperatures and high densities, and in understanding axions as dark matter, to understand how, if you have now ideas about unification, about fundamental theory, because the veil has been lifted and you can calculate consequences in Big Bang cosmology, new things open up in a big way, new opportunities. But before getting to that, I want to talk about a night to remember. That was in the summer of 76 or 77, I'm not sure which one of those, at Fermilab, where we were spending the summer break. It was a beautiful night. It was a hard day's night, though, because that day, my wife and daughter, who were with me, were both very ill. And so it was a very hectic day trying to take care of them. Finally, they went to sleep. And they looked so peaceful. I was very pleased and relieved that this was. And it was a beautiful night out. So I decided to take a walk. And it sort of looked like this. It was fantastic, very inspiring. And it was a time when the standard model, as we now call it, was reaching maturity. Okay? People were beginning to believe in QCD and very much believe in the electroweak theory. And many things have been checked. But one sector hadn't been checked. And I said, well, it's time to think about the scalar particle sector, or the Higgs sector. What about that? That was still kind of mysterious. In fact, people didn't know even very basic things. How do you communicate with Higgs particles? The building blocks of ordinary matter have almost zero mass, the quarks and the gluons. How do you get them and electrons, and photons, how do you get them to communicate with Higgs particles? Well, during that walk, I realized something that's now called the Wilczek vertex, at least by some people. And it was that Higgs particles can communicate with the ordinary world, but specifically by the gluons, which were the characteristic thing introduced in QCD, because the gluons can communicate with very heavy particles, and then the heavy particles can communicate with the Higgs particles. So by these kinds of quantum fluctuations, this kind of loop graph, this is the leading way in which ordinary matter talks to Higgs particles. And about 25 years later, this was the key to, in fact, discovering the Higgs particle. You produced it this way at the LHC, colliding gluons to make a Higgs particle, and then kind of a dual process where it decays through heavy particles back into photons. And the so-called discovery of the Higgs particle was actually this little blip here. It was statistical. Not a single event was identified as decay of things into a Higgs particle. It's a blip in the diphoton mass distribution. But the point I wanted to make with this is that it's only because of QCD and your ability to calculate what the background to this is very reliably that you could first of all, design an experiment to have the requisite sensitivity to just barely be able to pick that out, and also to interpret it convincingly. So that was, I think, should be chalked up to QCD at least as much as to Higgs. All right. Another adventure that still is pending, I would say, and in which Howard Georgi, Steve Weinberg, and Helen Quinn pioneered, is to take these calculations of how charges evolve with distance and to see if you could extrapolate from what we know about the strength of charges in our different components of the standard model to see if they would unify at short distances. And although at first the data looked very unpromising, as it stabilized, you see it almost works. with the known virtual particles included. But if you widen the theory to include supersymmetry at low energies, then it really works. It works within the error bars. And not only that, but gravity, which was not included, is rather a different character from the other forces, actually also comes in and joins them in terms of its absolute strength. So this is an indication that we might be on the right track. We might know all we need to know, all that's essential in order to figure out what's going on at ultra high energies, if only we were smart enough, which we're not. Okay. Unfortunately, at present, this is a big tease. The low energy supersymmetric particles that this suggests have not been observed. And we need to persuade the funding agencies that we need a bigger machine. Well, first we should persuade ourselves, but yes. Okay. So another thing that opened up when we understood the strong interaction is that we can describe the early universe, as I mentioned, in principle, if we straightforward in principle to calculate what goes on, and also what happens at very high density, and for instance, in neutron stars. And so there's a phase diagram for QCD, for extreme matter. So what happens at really extreme temperatures and densities, way beyond metallic hydrogen, which I heard about this morning. And a lot of interesting things have been discussed, but I'll just mention a couple of things that I was personally involved in, figuring out that this almost surely is a line of first order transitions that ends in a critical point with critical fluctuations that you can hope to observe. And out here, the phenomenon of color superconductivity, which almost certainly occurs at ultra high densities and might be revealed in the interior of neutron stars as we're able, using gravitational waves and picking up on in spirals or collisions of neutron stars, neutron star binaries to access the inside, deep interior of neutron stars. So there's a phase diagram from QCD. When I went to Santa Barbara in the early 1980s, I suddenly discovered there was something called condensed matter physics, and you could try to understand things like this. And this has been quite a fun adventure. And you see the crucial experiments to check whether there is a critical point, whether there is a first order phase transition. These are underway. And we await the results with, well, we better not wait with bated breath because we'll suffocate, but we wait the results patiently. Okay. And then now I want to decelerate again, go into a lower gear to discuss in some detail, perhaps the potentially the most brilliant outcome of QCD. These are axions. This is an ongoing, and certainly this is at present a field in ferment, an ongoing saga. For me, it began that same night. I was thinking about the Higgs sector, and if you had one Higgs particle, how it would communicate with the world. And then I said, okay, well, that's under control. What about if you have two Higgs doublets? What happens that's different? Well, one thing that can happen is you can have extra symmetry among those two doublets, and then you would get a massless particle when the symmetry broke. At the time, I was vaguely aware that Peche and Quinn, Roberto Peche and Helen Quinn had been thinking about this, and it had something to do with the theta angle in QCD, which was a very popular thing. But I thought to myself that such a particle would certainly have been detected, and I kind of put it on the shelf, didn't follow up until until a few months later. And I talked about it at Princeton. Kurt Callan heard me talk and was visiting Harvard, where he talked to Weinberg and asked, Weinberg, what are you doing? And Weinberg was working on very similar things, but he made a crucial mistake. He was calling these things Higglets. So we communicated, and I persuaded him that they're actually axions. And the reason that they're axions is an interesting story. A few years earlier, it really was just a few years earlier, when I was home from college as an undergraduate, I went shopping with my mother at a supermarket on spring break, and I saw on the shelf this laundry detergent, Axion. I said, wow, that really sounds like a particle. It's Greek. It sounds a lot like baryon or pion or muon. It's even got an ion, and ax is axial. It's very Greek. And I said, if I ever get a chance to name a particle, I'm going to call it an axion. And then a few years later, addressing a problem with the axial baryon number current, this particle arose. The chance arose, and so clearly the stars were aligned, literally the stars, and that's how axions got to be axions. Well, this was probably the most exciting acute episode in my entire career. I was convinced that axions, well, Steve convinced me that they wouldn't have been detected, but that they could be detected. And then, so we, this is a, well, I should, the axion theory, we didn't realize that at the time clearly, but people with initials like this did very shortly later, that actually the axions should be considered as a one-parameter family of theories. We originally had them at the so-called weak scale. This, in the one-parameter theory, you have the mass as a free parameter, but once you know that, you know everything else, including the coupling to photons. And so you have this plot of coupling strength to photons versus axion mass. This golden thing is what the axion theory gives. Actually, the KSVZ line is probably the more favored one, so that's a line under there. There are some theoretical and cosmological, and well, there's some theoretical uncertainties in this, but basically this is the allowed range. And what we had, and you can see that people have put a lot of attention into trying to find axions. It's a good idea. Everybody thinks so. They might have had doubts if it was called Higglets. Anyway, but you can see that the region we had originally is ruled out. It's buried. It's buried in these experimental limits. But fortunately, people realized that it's actually a one-parameter theory, and so you can maintain this the desirable features of having the axions without contradicting observation. Now, something dramatic happened in the early 1980s. The theory of evolution entered into particle physics. The basic axion framework had been you have this parameter, which for unexplained reasons is very, very small. And the goal of the axion theory is to tell you why it's small. And in the axion theory, you do that by minimizing an energy. So that was the way people thought about what you should do in particle physics. You should just minimize the energy, and that would be the ground state, and the ground state is where we live. But as the cosmologists got their act together and Big Bang cosmology got more credible, we took it to heart that that's not the right way to analyze things. You should analyze how things evolve from initial conditions in the Big Bang and what the consequences of a hypothesis about fundamental interactions is. And as I said, because of this change from 1972 to 1976, where the veil lifted, you can actually do these calculations and see what the consequences of fundamental ideas are when you run them through the Big Bang. And what you find in the case of axions is fantastically interesting and promising. You start with a field that has both magnitude and phase. The phase is this thing that you want to be very, very small. So it has to be along this line in order to agree with what's observed. But what happens dynamically as the universe evolves, you start from kind of a random value up here, but symmetry breaks and it has to roll down. So the massive degree of freedom, the one that has a steep descent, moves right down here. But the angle doesn't immediately move down. And the angle is the thing that you want to explain the smallness of. But as the universe expands, it does get very, very small, but it keeps oscillating. And the good news is that the amplitude of the oscillations, the uncertainty in the angle, is very, very small. The even better news is that those tiny oscillations that you can calculate can be considered as particles, can be considered as a background radiation filling the universe, and that it has all the right properties to make the dark matter of the universe, even though the theory had no reference to that problem in the beginning. This was not a fit, but a discovery, if you like. And so, in fact, the dark, I remember when I first heard about the dark matter problem, I said, well, it's amazing. The dark matter problem was at that time that the universe, by some measures, was a 1/3 of the closure density. By other measures, was the whole closure density. And I said to myself, it's amazing that they get it as close as a factor of 3. But cosmologists got their act together, became much more accurate, much more serious, and they had this discrepancy. This is a beautiful thing where you can measure the power of a galaxy here to bend light and make multiple images of things behind it. And this and many, many other observations show that we really need a new component to the universe that makes up 6 times as much mass as ordinary matter, but interacts very, very weakly with ordinary matter. And that's what axions can be. So I'm very tempted to say, or to ask this question, have we already seen axions? And that's a big question. And here's the answer. Yes, after a fashion. Not, unfortunately, the dark matter axions, but what are called emergent axions. These are things that obey the same kinds of equations as axions and exhibit the same kind of phenomena, but with different values of the parameters, and typically only within materials. So you would call these emergent axions. And a beautiful experiment here using, as you see in the title, the equations of how axions interact with electromagnetic field, axion electrodynamics, was able to get a measurement of the fine structure constant using an ugly material with 1% accuracy. It's a fantastic thing. And this morning I talked to Professor Zhu, who was doing experiments on which take this kind of emergent axion to another level. So congratulations. But I didn't have time to make a slide for it. Okay, so now I'd like to elaborate on the difficulty of catching a cab in New Haven, which is quite a challenge if you ever tried. But in this case, the cab is short for a cosmic axion background. And this is the kind of experiment we're doing to see if axions really are the dark matter of the universe. The basic coupling is, as I mentioned, you can predict in terms of the theory, it's a one-parameter theory, so there's an overall strength here, but otherwise it's completely determined, and the strength is connected to the mass, and the mass is connected to the frequency at which you get photons coming in this conversion process. So everything is pretty well pinned down. The equations are pretty well pinned down. And it's just a question of whether you can get the requisite sensitivity. You know how many axions are out there if they are the dark matter and given their mass. And this beautiful picture shows that they've traveled a long way from the Big Bang, undisturbed. They interact very, very weakly with ordinary matter. But if you set things up just right, with a big magnetic field, very, very occasionally an axion converts into a photon, and then your eyeball or a suitable electromagnetic detector can see it. So you need a magnet, a really big magnet, because the interaction is very weak. This is sort of reminiscent of neutrino experiments, but even more so. You need a big magnet. You need very, very sensitive low noise detectors, so pushing the limits of quantum technology. And what's been a particular source of innovation in recent years, in that box, you can put materials that encourage the photons to have properties that match to the axions, and so the axions can resonate and convert more efficiently. So resonator design, using things like metamaterials, and well, there's a lot of creativity that has and will go into doing better and better. And the result, this was something that I have been and am involved in, the so-called alpha collaboration, which is in New Haven, and that is actually mounting an experiment now that's going to get into the region of parameters here. This is the same figure now, just turned 45 degrees, that where the axions would be the dark matter of the universe, according to recent estimates. And you can see here that with existing designs, we've promised to deliver this over here. But I think we have enough tricks in reserve that we can cover this whole predicted range with more effort. In any case, there was a milestone very recently on, well, exactly 1 month ago, March 9th. We haven't yet got our hands on that really big magnet, but this is a pretty darn big magnet that just barely fit through the window of the Sloan Laboratory at Yale University, where it had been sitting unused for a while. And we moved it, we, meaning somebody else, moved it to a new facility, the Wright Laboratory, where this alpha experiment is going to be done. And so it's really happening. Very exciting. And so here you see, at our first collaboration meeting, I took the opportunity to show off a little. Okay, finally, I think I've overextended already, but I will finally mention one new adventure that's ongoing, trions and channeling. So let me ask, let's have a little audience participation. What's wrong with this picture? This is meant to be quarks interacting with each other. This was actually the picture that appeared on the Nobel Prize poster in 2004. And it is wrong because, come on, this is Harvard, right? No, because quarks don't have faces. No. Well, that's one thing that's wrong. But another thing that's wrong is that when you have color flux going from a quark, it can't end on another quark. It has to end on an anti-quark. The way you can have flux arranged so that three quarks can be confined, as in a proton, is not a generalization of what you have in a quark and an anti-quark. These are numerical simulations now that really do show the properties that we blithely assumed in the early days of confinement and so forth. But if you do three quarks, you don't get that delta, you get a Y with it. And this is very interesting. This is really super non-perturbative, non-abelian behavior, but it's very difficult to access numerically with existing methods, because, well, for technical reasons that are quite profound, quite serious. And there are lots of things that you would like to explore about these flux tubes and their interactions when they come together in triples, so-called, that's what we call trions. You'd like to explore those properties in detail numerically. So the bright idea that we're exploring is to have places where nothing is happening, don't calculate there. So in numerical simulations of QCD, you're permitted to maintain gauge invariance, all basic principles, and just put the coupling to 0 outside regions where you don't want anything to be happening. So you can create a true void, not a quantum vacuum that's fluctuating, just a true void, nothing is there. And then if you have the flux coming out of quarks, it can only go where you've allowed things to happen. So you have channels where the flux is permitted to go. And that enables you, theoretically, to study, for instance, how two trions interact when they sit right on top of each other, which otherwise would have been totally inaccessible, how two flux tubes interact when they're right on top of each other, or how a flux tube interacts with a quark, and many other things. So fundamental properties of QCD, or I should say of non-abelian gauge theories, can become accessible to numerical study. And then finally, the granddaddy of them all, I should mention that there are material analogs of these things, emergent channeling. G goes to 0 in the non-abelian theory is equivalent for electricity to the dielectric constant going to infinity, or for magnetism to the mu going to 0. I can never remember, it's permeability or whatever it is. It's either permeativity or permittivity or permeability. You pick. Anyway, the perfect diamagnetism channels magnetic fields into the channels. So if you have a superconductor with holes drilled in it, that would implement channeling for magnetic fields. So that's fun. And finally, I want to return to where it all started with quarks. Quarks, we said, are not observed in isolation, and that's true. And the theoretical understanding of that is you have a quark, it has flux coming out of it. If it's isolated, there's no antiquark, no two other quarks. There's no way for the flux to end. It just has to keep going. And that costs an infinite amount of energy because there's a finite amount of energy per unit length. But if the quark is surrounded by void, the flux can just stop. And so you can have quarks in isolation. And you can see as you expand the region around the quarks, what does the flux do? I don't know. But it's certainly an interesting question. And we'll look forward to further adventures in QCD for the next 50 years and more. Thank you.
Thanks for a beautiful talk. Any questions? Yes.
Yeah. I have a question for you, Frank. You've written a very couple of interesting papers on the noise of gravity.
Yes.
So can you talk about the experiments? Is there any planning? Because it sounds quite intriguing. Like to do a follow-up.
Yeah, well, this is completely, completely different from the talk. I've had a life outside of QCD too in physics. And among the rest is some ideas about gravitational radiation and its quantum nature. And there's important follow-up work or even fundamental work to be done in that direction. I don't have anything concrete to share at the moment, but I'll tell you what I'm looking at because it's kind of poetic, especially here at Harvard. Most, or I think all, modeling of gravitational wave fields as quantum objects has assumed that they are coherent states, either explicitly or implicitly, because that's the closest you can get in a quantum realization to a classical field. And it's also what you get if you have linear coupling of a source, say an energy momentum tensor to a graviton. So if you have a linear coupling, that's what you get. But the gravitational wave sources, especially black holes in their final throes, are not linearly coupled. The gravitational self-couplings are very strong. Now, Roy Glauber, in the context of electrodynamics, proposed precise tests of whether a state is coherent or not. And that kind of, in some ways, founded the field of quantum optics. You can building on that work, you can make null tests of whether the gravitational radiation field is a coherent state or not. So that's in progress to see. And it's a different technology, so the actual experimental protocols would be different, but the theoretical framework that Glauber constructed in the context of electrodynamics suggests the way forward also in gravity waves. Yeah.
Yes.
Was there any idea that the proton had substructure before deep inelastic scattering?
Yes. Yes, there was, before deep inelastic scattering, there was elastic scattering. and particularly relevant was the work of Hofstadter and others looking at form factors of protons. So this was directly extending what Geiger and Marsden have done, just to larger momentum transfers, not inelastic, but elastic. And that's called measuring the form factor of the proton. And that already showed that the proton was had a non-trivial charge radius that was, so people knew empirically that the proton was an extended object already.
So what was the jump that proton has substructure to protons made of quarks?
Well, quarks are a very particular thing, so quarks have an interesting history. In the 1960s, there was an explosion in the discovery of new strongly interacting particles, so-called very unstable particles, mostly called resonances, and they had to be classified and organized. And Gell-Mann especially, and Zweig and others found the way to organize this data based on a picture of what these resonances were. And in retrospect, it's kind of just a generalization of how we understand atomic spectra. Atomic spectra, we understand where you can have a nucleus and then you have electrons around, and the electrons can have different energy levels, and that's a spectrum. The difference, and the quark model is basically the same idea, but now you have, instead of electrons, you have just something called quarks. They have spin 1/2. They have other things, and you can analyze them as quantum mechanical objects in the presence of a bag or confining potential. People were pretty vague about what the forces were, what was I going to say? Oh, so the big difference from atomic spectra is that because the energy differences are so large in hadronic physics, it wasn't obvious before the quark model that excited states of protons were actually excited states of protons with internal vibrations and things like that, as opposed to completely different unrelated particles. But the quark model made it clear how to organize things. But it didn't have precise equations, and it also had bizarre rules. The bizarre rules were that you could either have particles that were a quark plus an antiquark, or you could have 3 quarks, but nothing else. You couldn't have individual quarks or 2 quarks or 2 quarks and an antiquark or anything, just that's basic mesons and baryons, and of course, antibaryons. So there was the word quark and some hints that they should be spin 1/2 particles, that they should have maybe a color degree of freedom, that was not so clear, but no equations. So no, how should I say? No equations that you would be upset if their predictions were wrong. That was the real innovation of the new QCD. You had equations that you would be upset if they didn't work. Yeah.
Yes.
Yes.
Well, you're going back to the early universe.
Yeah.
And the question is, does QCD say anything about the Big Bang and the singularity?
Well, okay, it says a lot about the Big Bang. It says not much about the singularity. So as I said, it enabled us to peel away the veil and look back with confidence into the very early moments of the Big Bang, beyond fractions of a second, small fractions of a second, and with some confidence. And so we could start to build models of how matter might have started to dominate over antimatter, about how axions got produced, other speculations. Yeah.
Would that also relate to the quantum gravity problem? That is, as you're going back to the Big Bang?
Well, if you keep going to, okay, so QCD and the rest of the understanding of the standard model gives you a pretty secure picture of what the universe looked like back to temperatures of 10 to the 14th or 15th Kelvin, something like that, but it's getting hotter. When you get to 10 to the 32 Kelvin or so, then you're in trouble. Then quantum gravity starts to come in, and so it's a different question. I mean, and other than so. QCD allows you to pose the question and sort of isolate it, and this unification of couplings calculation encourages you to think that it really ought to be possible to understand how gravity works, and that maybe it does become unified with the other interactions, but it doesn't give you any direct usable clues about how, I mean,
okay.
Yeah, any direct usable clues about how to proceed with quantum gravity. Now, if you're smart enough, you can figure out string theory or something else, and maybe you could get a usable theory of quantum gravity that certainly would be informed by QCD. Actually, that's an interesting case. String theory would be inconceivable without QCD. It came from a wrong theory of the strong interaction. Okay, that was repurposed to be a grander theory. That was what included. Instead of being a theory of hadrons, which was the strongly interacting particles, which was its original intent, it was repurposed as a theory of something else, including gravity. Well, I don't. That's the relationship of QCD to quantum gravity is fairly indirect. I would say it's more the inspiration that we can understand things, as opposed to any direct clue as to how to proceed. Yeah. Okay.
Well, let's thank Frank for a wonderful talk.
All right. Thank you.